Hello, my name is Harshil. I'm the CEO and founder of Dendrite. We make software, in short, to help compensate for a number of the things that we're about to talk about. I purposely created this presentation because in my travels, I kind of discovered that there's a lot of this knowledge around materials and process development that's been kind of hidden away or is just kind of locked up in a bunch of people who have been working in the industry 14 plus years. And my thought was, why don't I create an opportunity for people to just kind of learn about a lot of topics at a very high level, and then also honestly provide the links to the papers and things so that they could dig in deeper as they so chose. So, starting off, right, just to give you some context from my perspective, my goal is to fundamentally change how geometry is represented, transformed, and transmitted on a computer. Right, and that could be anything from reading in geometry, modifying it, slicing it, compensating for it, and then ultimately, sending it to a machine. Right, and all of these things are important because the amount of data that's generated, especially in this industry, right, is really important. So, what's the goal of this talk? Right, it's to try to dig into how can we expand the envelope of what's possible, right, from a material standpoint, from a part standpoint, from like a build rate standpoint. It's all about that, and this becomes ever increasingly more important as customers kind of go from a basic prototyping to production workflow, simply because once they can finally print something, the next thing that they want to do is print it reliably, repeatably, and on a bunch of machines, right, which is where a major source of variability starts to kind of come in, right? And so the idea is, okay, what can we do by acknowledging what's out there to kind of expand this envelope, right? And by expanding this envelope, inevitably also expand the TAM, which is, I think, kind of important here. So what are the key expansion areas? So, new materials, like in what regimes can they be used? Can we do multi-materials, printable parts, right? And that could be like small parts, thin walls, all kinds of those like interesting geometric features. The quality of the part, so like how heterogeneous is it, like what are the surface profiles, and of course, ultimately, things like flexibility aids that like maybe we can print the part without supports because we're doing something interesting. So the current state of affairs, I think, as you know, is there's just kind of a lack of education in this space due to a variety of reasons. A lot of this kind of knowledge is kind of tucked away by the machine manufacturer, and I do believe that if the end user knew more about this, they'd be just more educated about their manufacturing production process. This is just kind of motivating the talk. So, kind of doing a kind of deep dive, right? There are a number of challenges on the machine, the process, the material, and the geometry itself. And each of these things requires some kind of a compensation in some way, shape, or form, right? And what I'm going to do is I'm going to do kind of a survey, but a little bit deep dive on what some of those challenges may be and what motivates them and why they exist. They're all basically based on the physics of the process at hand. So, when we're talking about jetting, right, depending on what print head you're using, there are a bunch of pros and cons to a number of the print heads, but a number of these print heads are also trying to solve a number of the issues that I'm talking about, like firsthand, right? But if they can't solve them or there are difficulties, right, there are opportunities for software to go solve them. So the first kind of category of jetting related problems are basically all related to variability in what droplets are coming out, right? So in a traditionally 2D printing process, right, the paper or the material moves past the print head, right? In this industry, it's kind of the opposite, right? We have the paper or the substrate, there, and the print head is moving past the material, right? Print head's moving means that there's a dynamic pressure behind the print head, and if the print head is not set up to handle that, it means that there is a dynamic droplet volume difference as the print head is actually moving, right? Moreover, of course, there are crosstalk related issues. So crosstalk can be acoustic or fluid related. Basically, when there are nozzles that are next to each other, depending on which nozzle is firing, it might actually affect the droplet volume in adjacent nozzles. There are also just droplet size limitations just due to the physics of how a print head works, right? So nozzles work by basically oscillating a piezo, right? The frequency controls, how much of the droplet volume is coming out. And because of that, we're basically dealing with a full acoustic system. So we have all kinds of resonance-related things, like things, of course, don't like instantaneous jumps in droplet size or volume. So what this is all kind of coming together to say is the print heads are fantastic. They can do all kinds of really cool things, but inherent to their physics, there are limitations that you just kind of want to know about that kind of constrain how you want to kind of deal with them. Beyond that, of course, we're now getting into density variation. So it matters how much the droplet of whatever you're jetting, penetrates, right? There are all kinds of different binders that people are developing. One number that you should be aware of is Anisotropic number. Basically, it's a relationship between the viscosity and the surface tension. Right? Think of as you're dropping material through those print heads, right? They're going under an immense amount of shear, right? And in order to make sure that something is jettable, there are all these chemical constraints, right? And they're all, again, related to the physics of that. Moreover, this also relates to, again, that droplet volume problem. There's also density variation due to ballistic effects, right? So if you are jetting and that droplet hits some substrate powder, that powder could fly away for some reason, right? And so you need to be able to control for that. There's also density variation due to binder bleed. So most people talk about bleed in the XY direction, kind of like a blooming thing that's going on towards the edges, right? And that's why you might try to do some kind of feathering or compensation towards the outside edges. But bleed is also actually in the Z, right? Like just like in a photopolymerization process, there's over and undercure, right? Like there is a Z bleed, and of course, if you have a surface towards the edge and there's a downward facing normal there, right? You don't want it to bleed through into the substrate, right? Moreover, again, getting into like why some of these things are important. There are a number of people who are also concerned about weak green parts. In order to make an automated depowdering process, we need to make sure that the green parts are stronger and better, right? This can come down to powder formulation, this can come down to binder formulation, but ultimately it also comes down to how the heck do you put the droplets where you need to put them. There's also, of course, the actual burning process of the binder. If you don't need to burn it, why put it down? And then finally, of course, there's a whole host of things related to part shrinkage that I'm not even going to get into because there are so many other folks kind of talking about it. So at the end of the day, I know I just kind of rushed through a whole blanket survey of potential issues and things that you might encounter when you're designing a machine with a print head. Right? But the key, from my perspective, is it all comes down to basically droplet volume control, depending on where you are within the part, right? And it's all based on, of course, the printhead limitations, though the printheads are getting much better every single day. But it's also importantly based on what binder you're using, what powder or substrate you're using, the print speed, and ultimately the geometry behind it. Almost every talk that I've gone to in the last couple of days, whenever anyone asks the question, can you avoid this? The mealy-mouthed answer from the presenter is basically, well, it kind of depends on your application, what your geometry is, right? And that's ultimately kind of the hardest part of the scenario because as a machine builder, right, or a printhead manufacturer, you can try to optimize the ever-living heck out of whatever you're doing from your machine standpoint or your printhead standpoint. But ultimately, the customer who has some geometry that they want to go make, A, they probably don't want to share it with you because it's their IP, but B, that customer needs the tools necessary to go that final mile kind of from a compensation standpoint. So there are similar things in the photopolymer world, right? If I don't have a degree in chemistry or chemical kinetics, but I've interviewed a bunch of people and kind of learned enough to be a little dangerous, right? But it all comes down to basically temperature and light and monitoring what's going on with the reaction, right? Long story short, temperature varies. It varies along the bed, it varies in the part, right? It varies in Z, right? And the more you can control this, the better, right? But of course, there are physical limitations to that whole thing. One thing that I've noticed that I haven't honestly seen from many photopolymerization folks is the concept that the temperature on the outside wall of the part is actually different than the center core of the part, right? Because there's a reaction happening here, right? From what I've learned and seen, there are minor temperature differences can lead to major differences in material properties, right? And there have to be ways to kind of compensate for this. There's also a whole host of issues related to light input variations. Not only differences as they're made, but over time, the window, all that good stuff. Then of course there's also the whole host of issues related to overcured, undercure, and just kind of penetration. Again, I have basically this talk on our website with all the papers that are being cited here, so you can definitely dive in way deeper. But this overcure, undercure thing is actually getting even more interesting because more people are putting things in the resin, right? They're putting particles, fibers, whatever, right? And that only complicates this whole scattering problem that needs to be solved. But Again, what's the key takeaway in all of this? It's all about, even on the photopolymerization side, controlling the light intensity based on the location, the light engine variance, the bed temperature variance, the resin material, but ultimately the geometry being printed at hand. It always comes back to the geometry on the end customer side. And so, what's the goal here and what's the solution? Well, there's obviously printer level, bed level compensations, there's light engine level compensations or printhead compensations. There's material-based compensations, right? This can all happen, a priori to the customer at the machine building or, product specification phase, but then there are also these geometry compensations that need to happen downstream. What does that mean from a software perspective? Basically, all the processes that I just talked about today take in images as an input, whether it be PNGs, like bitmaps, or TIFF files, whatever it is. It's basically a bunch of pixels with a bunch of colors. Right? Traditionally, most folks are using a pure monochrome image. Right? There are some folks who have been branching out a little bit into the grayscale image, but ultimately, you need as many bits in the grayscale as possible, and that's conducive to the process, and potentially even RGB. Right? And those color variations in the image basically control droplet volume and light intensity on a location basis. So I just talked about these general compensations, but I figured let's kind of go into what does it mean to compensate the part, right? So there's nothing magical happening here. Basically, you want to know how far inside the part you are, and you want to know what's the angle of kind of the nearest surface. And based on all of this information, you want to control basically the color of the image, right? If you're talking about it from like a laser powder bed fusion standpoint, that would mean upskin, downskin, and inskins. But it gets more complicated than that because you want to probably have a gradient as you're going out, right? You also don't want big discontinuities because that could also lead to weird issues from a material homogeneity standpoint. Moreover, of course, I think that a number of people are aware that you can use gray values or different kinds of bits on the edges to help with anti-aliasing. So what's one way to go do this? Well, one way to go do this is to take a GPU and smash it against the geometry and do a full 3D volumetric analysis of the geometry, right? So here's one example of us taking a propeller, basically doing a voxel operation on it to look at everything. And then what we're actually doing is we're coloring the geometry based on how far inside the part you are and the normal vector and angle of the nearest surface. Right, here's another example. So this part is a part that you might recognize out of UTEP. It's a test specimen. And basically, when I zoom in here a little bit more, like looking at a specific slice, the red, just for demonstration purposes, is an in-skin. It's basically graded based on how far you are in the part. The green is a downward-facing surface, and again, it's graded, kind of like an onion with lots of little shells. And the blue is an upskin, which is, again, based on the normal vector graded. And the whole idea behind this is, on this particular one, I think there are 17 colors. Basically, the idea is on a per color basis, you can apply a completely different process, right? You can have a different light intensity, a different set of droplet volumes, a different type of dithering. If you're in laser powder bed fusion, you can apply a different laser speed, focus, etc. Like the key is you want to be able to volumetrically segment this geometry and then apply different things in different areas. This is not necessarily a new or profound concept because if you're coming from the CNC subtractive world, right, you have a roughing place and then you have like a Klein milling place where you want good surface finish in certain areas, but you want to rough it in the center so that you can get as much throughput as possible. It's basically the same thing, but done at a much higher, more complex scale given the sophistication of all the processes that are kind of in the audience. Another example of this is kind of with the Stanford bunny, right? So, the next thing you're probably wondering is, okay, well, now that I can do all this complicated analysis, how the heck do I tune all these parameters? Well, you need essentially a way to do quick designs of experiments on a per material or per machine basis. And so what you're seeing here is different volumetric segmentation paradigms going across the board on all four bunnies. Okay. So I basically just have a bunch of more pictures here, talking about different ways of adding grayscale based on the type of geometry, where you are in the geometry, whether you're inside or outside, or maybe like, for example, you're putting a lattice and it wants a different process as well. We also have ways of doing kind of like anisotropic compensation, again, based on where you are in the geometry and what you're doing. So here's kind of an example of a fluid channel. You have to like really zoom into the picture to see kind of what's going on, but you can see that there are major differences in the compensation because you can see the rings changing. Again, we're talking about compensating microns here, not major bulk areas. And yeah, I mean, there's so much to go into this. Almost every little sub-bullet I gave you is probably someone's PhD in some way, shape, or form. But the idea is, you know, this is a topic that I'm personally trying to evangelize and educate more people about, and honestly give them software tools to get a better grip over it, and honestly start experimenting and figuring things out. I'll take a few questions before handling it over to Gareth, who's from Czar and can talk more about the printheads, but I'll maybe take a break because I just did a huge information dump. So, any questions so far? Yes?
I think it goes without saying, to do almost everything you're talking about, you have to do direct from CAD slicing.
So,
because I don't see how you can do any of this if you're using an STL or even a 3MF in the middle.
right. So it's yes and no, and I'll try to give a mature answer, even though I fundamentally hate the fucking CAD and 3MF like the STL 3MF nonsense, right? So what is an STL file, right? It comes from CAD data. It's just simply a linear tessellation of that. A 3MF is honestly not much different than an STL. It's just the geniuses who made the 3MF decided XML is a great new format and wanted to fix some of the issues. But ultimately, we can actually do this geometric analysis on an STL as well. Now, there is a difference though, because when you have the CAD data, you can actually get even more important metadata, right, associated with the surfaces, and you can be clever about how you look at the resolutions, right, because traditionally an STL or a 3MF is exported at one sampling resolution. But no, you could absolutely do this on an STL or 3MF, but you could certainly do even more with CAD data. Any other questions? Yeah.
There was a slide that you're talking about 10-layer Boolean, like traditional OEMs do a 10-layer. Can you talk a little bit more about that and what's the difference between what you're doing and what traditional OEMs do?
Yeah. So if you look in, for example, laser powder bed fusion, right, the new. So I had a slide here. Let me go back to it. Right here, where we talked about how the way this geometric analysis is currently happening in the industry. So if you're looking at laser powder bed fusion, right, you've heard all this fad nonsense about support-free printing that's been around for decades, right? Basically, how do they even get there? So at a given slice, someone will look up 10 layers and down 10 layers, okay? And what they'll do is they'll take those layers and they'll subtract them from each other to try to see what's overhanging and what's underhanging, okay? So that's inherently a 2.5D approach, okay? And yes, you can see what layers have powder underneath them and which ones don't, or what layers have already been cured or whatever your process is. But fundamentally, that's what they're doing to figure out what's up and down, okay? That process is error prone because imagine you had like a fin and that fin ends abruptly. Well, when you're looking 10 layers up above the edge of the fin, what's going on, right? It's pathological, right? There are lots of little cases like that where this 2.5D analysis approach was super nice when we didn't have great computers, but leads to all these pathological issues. What's the difference between that and what I'm talking about is we do a full volumetrics approach. So instead of doing a layer-wise thing to figure out what surfaces are facing upwards and downwards, we just look at the surface and say, hey, are you facing upwards and downwards? And then project inwards, right? What that means is, because, like if we looked at the top of a fin surface, we would know that this surface is pointing directly upwards, projecting downwards, and in the fin, like here, I'll see if I can maybe even kill this and just zoom into the picture more. It might make it even easier. Let's see. All right, so I'll just project my voice. Basically, this is an example of a set of fins, and you can see here that there are multiple colors of red here, right? Here, there's only really one color of red, but here, they're up to 5, right? What this means is we're able to analyze how thick and thin the fin are, and because we have the information about the top of the fin, we can be more sophisticated about it in a 3D sense, because all these compensations essentially relate to the part and interface between the cured, the jetted, or the fused material, and the rest of the material that hasn't had that process. Does that make sense?
Wouldn't you know this just from like triangles and numbers?
Yeah, that's why I said you can do that with an STL file. The point I'm trying to make here is most people, when they do this analysis, they're not doing it from the triangles or the CAD data, they're doing it from the layers. But that's correct. Yeah.
When you talk about compensation, are you pairing with simulation software or scan data from printheads? Can you talk a little bit more about that?
Yeah, so us in particular, we're a wholly geometry company, right? I mean, even though my PhD is in fluid mechanics and I can write you a simulator in Fortran, our goal was specifically to stay away from the physics, and it's due to two reasons. Number one, that's where all your IP is in some way, shape, or form. It's all around the metallurgy, the polymerization, the chemistry of it all. And my goal was to simply provide you the best math engine possible so that you could apply those compensations. Number two, that's why we're partnering with folks like ANSYS and Altair, who want to write their own simulation versions of these things so they can apply the compensation. So think of it as the tool for analysis and compensating, but it doesn't have the brains to know what to compensate it with, right? And the idea was to give the tools to the machine builder so that they can make that IP around it. Does that answer the question?
Yes.
Any other questions? Nope. Okay, so I'll flip it over to Gareth then to talk a little bit more about Czar and kind of dive in a little bit deeper on some of the jetting stuff. Let's see. There you go.
Thank you. Thanks, Harshil. So we start with who's heard of Czar, I guess would be a good starting point. So one question I get asked an awful lot, and I feel I should clear up, is that Stratasys do not own Czar. They bought a subsidiary of Czar. So what is now the SAF technology was developed with Czar, with Professor Hopkinson in the University of Nottingham, and that technology has gone to Stratasys now. They bought that company, but the main PLC printhead business unit is still a fully independent PLC making printheads. So just to clear that up, save me saying it 100 times this week. So a bit about me. I started as a tool maker. That's my training. I'm a mechanical engineer. I joined Czar to prototype electromechanical systems to make printheads. In doing that, we had a very short time scale, and to supply fluid, mounting points, and mechanical structure to a printhead, new type of actuator, I used 3D printing, and it enabled us to get results in months, which would usually take years. So evaluated the industry and spent a long time determining what was best for printheads, and printheads are a really good example of a mix of engineering disciplines. We've got fluid dynamics, mechanics, electronics, material science, even civil engineering in the factory. So we've got a company full of really clever individuals, and they're fascinating things to work on. But I chose to specialize in 3D, so this is my 5th AMUG. I've learned an awful lot here, and my email address is at the bottom if you've got any further questions after the talk. Just come up and approach me. Pushing the boundaries of inkjet, it's a bold claim, right? But we'll see where we can go with this. So in 3D printing, there are a large number of companies already using printheads of one form or another. Czar included at the bottom there. But the beauty of printheads is they can carry a very wide range of fluids. So we can do ceramics, metallics, fluids that turn thermoplastics into solids, and thermosetting plastics as well. So we can work on the entire material set that's available. This image on the screen here is printed with a photopolymer from BASF, and it's jetted at 40 millipascal seconds at 50 degrees C. So the printheads that Czar make are capable of jetting higher viscosities than inkjet usually is. And the reason for that is, we'll dive into a little bit of the way the printhead works, is that we have a recirculating printhead with a high flow rate. It's true designed in recirculation rather than added on, as it were. And the fluid enters the inlet in the center, travels across the piezo actuators, and travels out of the outlet. The restriction to flow is very, very low in this head. The nozzles are actually on the bottom of the actuator, so here. That pointer's not working. The two trapezoidal sections at the center of the smallest edge is where the nozzles are, so the droplets are jetting down as you're looking at it. So the ink has a very high flow rate, as I mentioned, 100 to 150 milliliters a minute. That flow rate becomes the dominant fluid mechanism of our print head. It actually means you can mount the print head on a 6-axis robot and turn it into an end effector. We can jet upside down if we want to. So you could consider non-planar 3D printing with a print head if you wanted. The fluid's constantly moving in our heads, which helps prevent sedimentation of particles and enables very high particulate inclusion by weight for a print head. Up to 60% is our record, but that does require some very good ink formulation. We're self-cleaning, so the recirculation means that any agglomerates of particles, any large debris bits, any air bubbles that are ingested through mechanical shock, they all get pushed around the print head through that dominant fluid mechanism rather than getting locked in the nozzle and stopping it jetting. And it's self-priming, so the nozzle is continuously and constantly fed with the same pressure and flow conditions and temperature conditions, and it's in parallel across every nozzle on the print head. So you get very good volumetric uniformity. This helps reduce latency, so you can leave the print head longer between capping it and maintaining it. And like I say, we jet at a constant temperature, so the conditions are consistent. A bit about the high viscosity jetting itself. So Harshil did a good job of laying out the basics of the physics. But typically in inkjet, the owner's organ number is less than 1. And the limit of inkjet across the various manufacturers is up to 25 centipoise, and that's anything from 1 to 25 across various manufacturers. So our range on our GS6, our 6 picoliter product, is about 8 millipascal seconds or centipoise to 100 millipascal seconds. And that's standard graphics mode with the standard speed and resolution that we have in the product. We have a mode called high laydown mode, which operates the piezo at near resonant frequency. That chucks out a lot of drops that are very fast, that are very big. The 12 picoliter product will fill a Starbucks grande in this mode in less than 3 minutes. It's an awful lot of fluid, and you can lay down 80 micron layers of photopolymer. So what does high viscosity enable? Well, in photopolymers, it enables function. So you can start to put in toughness, flexibility, elasticity, high heat deflection temperatures. We can also engineer the polymers to have clearer definition between the part and the support material, new types of support material that dissolve away better and faster. So the hand you're seeing there has had no polishing at all. That's straight out print head with support material dissolving away. There are benefits in electrical and thermal properties as well. And again, the particle occlusion I mentioned, you can put fillers in, or those particles can form conductives or dielectrics or ceramics, so you can increase stiffness and reduce shrinkage. And it's not just 3D printing, this is the additive manufacturing users group, right? It's so additive literally means adding something to something. So we can also jet paints, coatings, biomedical applications, semiconductor, photovoltaics. And in its truest 2.5D sense, this is a drinks glass, a tumbler, printed with a UV photopolymer. The texture is a new product from one of our customers that's aimed at allowing customization in the embossed glass decoration field. That Fanta logo is just over 1 millimeter tall. It's 7 to 9 layers. It takes less than a minute to print that in high laydown mode. This photopolymer has been engineered to withstand all domestic and industrial washing criteria. So we're enabling function, we're enabling fast turnaround, we're enabling industrial manufacturing. If Todd was here, he'd kill me, but it's an industrial product. So that's all well and good, that's great, but how do you work with Czar? Well, we're an independent printhead supplier. So we are very conscious that in order to, and as I was reminded actually, getting a fluid out of the printhead is actually only a third of the problem. You have to get the fluid doing what it needs to do on the substrate, and then that unit needs to be maybe post-cured afterwards. So we need to work with partners to be able to provide a solution, which means making ourselves accessible. So we have a 5-step process, the first 3 of which are evaluation of the fluid in the lab to see if it will jet from the head. The second is tuning the waveform of the head for the application. So in this industry, you're going to be more interested in volumetric uniformity across the head than pure graphics quality or ultimate speed. The reason for ultimate speed not being important is there's usually a secondary process which is slower than the printing. So you're usually operating within the capability of the printhead. The third is sample production. So we've got several printing rigs, including a photopolymer 3D printer with 2 materials on it. So we can produce samples for you. So you can take a physical evidence to a stakeholder and say that this is real, and Czar have been great to work with. And we make ourselves accessible. And the 4th step is then first stage CapEx. We've got a development kit, so you don't need to buy a full 4-color, 4-material industrial machine to test and grow your capability in your company. You can buy 1 printhead with ink system and drive electronics, and we'll help you build your capability and your jetting understanding of how the printhead works and your jetting capability. And that's actually the 5th step, is the continued support. So we've got solutions which you can go from lab scale right up to full machine integration. If we don't do it, we've got partners that do. And for that full machine integration, you need to be able to complete the picture of supplies. That's materials, drive electronics, software. So we're working together with companies in all areas, Dendrite being one, to enable people to approach Czar and get the solution they need. We're supporting them with their application to get to end market quicker, using our expertise. We've been around 30 years. We make printheads in the hundreds per day in the UK. And our support network is unparalleled. So, as I said, partnerships are really important. We make a component in a machine at the end of the day, but the component has some unique capabilities. In order for everybody to maximize their access and capability to use the component, we need to work with experts in the other areas. So you announced yesterday Meteor have joined the DDC. We're in the DDC as well. So like I said, all our companies are open to working with everyone, but we are all working together to provide a solution end to end if we can. Simply, this goes right across our business, 3D, 2D. It's a world where you can print anything. The printhead is now no longer a device for printing pictures on a large scale or a desktop. It's a manufacturing tool that can jet manufacturing materials, and we're seeing more and more customers achieving that and driving towards that. So I think at a high level that's me done. It's time to take questions if anyone's got any. No? Lovely.
All right. Thank you, Gareth. So I'll also just add some more color to what kind of Gareth is saying, pun intended. So the DDC is the Dendrite Developer Council. It's a group of folks that we've been working with for quite a few years now. As he mentioned, Czar joined last year, I believe, and as of Saturday, it's official that Meteor joined. Right, we are working to provide whole solutions so that it's easier to develop jetting technologies, right? Solutions where the software, the drive electronics, the printhead all come completely integrated together. So if you're a researcher or just trying to develop a new machine because you're a chemist or a material scientist, like we're trying to make that bar as easy and simple as humanly possible. If you have more questions about any of the stuff that I talked about, please feel free to come up and ask me. If you have questions about the printheads, please ask Gareth and I can direct you to him if you like. If you're interested more about all of the volumetric segmentation stuff I kind of just teased a little bit, we can just give you a live demo and answer all your in-depth questions. We're a pretty open and transparent company. It's one of our kind of core values, and we're happy to dive into as technical as you want on a per process basis. So unless there are any questions, thank you for attending the talk. I hope you found it useful, and If there's any information you think I'm missing on here, please let me know, because I'm trying to honestly make it a knowledge base so that more people can easily get into the field and just understand, all the basics. So thank you.